Hi, very good evening, everyone. Thanks a lot for joining for today's session, which is day one of electric vehicle subsystems and technology. As a part of it, we will be covering the cells for attractive applications. So I'll be delivering the session today. Uh, it's me, Suraj, on the other side, who's joined on the Zoom and also streaming on YouTube. Thanks a lot, everybody who have joined here till now, and we're expecting many more participants to join in some few minutes. I believe you have received your, I believe you have received the email, uh, and I hope you have all got the links. And if you haven't got it, so please do. The people who have got it, please do share it to your friends, so they can also join in quickly. All right, just before we start our session in another 5 to 7 minutes. Let's just have like a quick interaction to sort of understand, what interests you to take part in this session or series of the sessions upcoming for this next 5 days. Maybe you can just drop your interest that what you'd like to learn and what interests you to learn about the topics and technology as a part of it, so that I can just try to magnify the part of the sessions to make it more useful for you. So any one of you or any of you can just drop your the purpose and an interest to take part in this sessions on the chat box. I would read them and try to understand to make it more useful of this for the sessions. All right, so very good evening, everyone. Ranjit, Sudhakar, Rakesh, Venkat. Awesome. So glad to see, I think, people across the country. And it was very overwhelming to see that even the session has reached many participants from other countries as well. We have some participants even participating from parts of South Africa, also from Nigeria, and many other places, and many also students out of the country participating from foreign universities as well. So quite excited to see the people interested in EV. Glad to know. Uh, Great. So I could see one interest from Barhadish Suresh, motor control and BMS. Interesting. Awesome. So I think that part of the session for tomorrow, yes, we will cover up on the battery management system. Definitely. Great. So hi everyone else who is here. So any specific interest that you would have to take part in this session? Mohammed, I would definitely take that as an input. I will surely look forward to make certain changes in the upcoming sessions for sure. To start at slightly in the evening, definitely. So great. So Mazika BS have an interest in battery management. Awesome. It looks like a lot of people have interest on battery management system. Torque request calculation. Awesome. I have my colleague, Mr. Krishna, who will help you to understand those concepts. On Friday, it will be a hands-on session. You guys can have laptops. We will run you through an Excel-based calculation so that you can basically perform torque calculations for vehicle and tractor requirements. Definitely, that will be on Friday. Revolution of EV in the world. Great. Awesome. So control system in EV. All right, Jagdish Gowda. We are very much interested to cover that. I think it may be slightly out of the scope for this topic, on and foundation. But I'll surely take that as an input and try to come back to you on arranging another session. Battery cooling system. All right, so that's interesting. That's interesting. I'll surely look into that battery cooling system and control system of EV. Great. So to know where EV domain is suitable for me. Okay, that's very interesting. Power electronics. Awesome. Fantastic. So it looks great, and amazing set of people from various backgrounds of interest on thermal systems, solid control systems, and majorly everybody is likely to be interested about battery management system. And that's a quite happy thing to know. And also there are other technologies too. You guys should be very much interested. Definitely the battery safety, yeah, predominantly a very important factor today. Specific to cooling system, definitely I'll try looking deeper into that in the upcoming days. All right, so EV is indeed interesting. Great. Okay, awesome. Lithium-ion technology, powertrain, battery fast charging system, awesome. Upcoming solid-state battery, fantastic. Awesome. I think that's a very comprehensive set of interests and inputs to me to take part those things to come up with an upcoming series of lectures or arrange some subject matter experts from India or other countries to deliver the sessions, simulation libraries. Fantastic. I think that's something I can definitely do in the upcoming sessions. Maybe simulation libraries. Yeah, certainly. Awesome. So great. I think it's just 5 right now, and it's 1 minute to go. But I think we should be good to start our sessions. All right. Good evening, everyone. Thanks a lot for joining in this course. That's a 5-day foundation to electric vehicle subsystems and technology. As a part of the day one, today we are talking about cells for tractive applications. And this is me, Suraj, who is the course director, and I'm also the co-founder and CEO of Decibels Lab. So I would not waste any time talking about Decibels Lab because pretty much you would know about us, or possibly you will come across to know about us by learning through it. So in simplified way, what we do, we create a quality learning content, and we help engineers to gain skill sets that are very specific to EV, not just as a skill set by doing many projects as an opportunity to gain an experience in EV so that you all can, get a good opportunities to land in amazing jobs and get paid well for it and create an ecosystem with technology so that we all can see better vehicles coming to the market. Great. So that's with a simple line of it. I would just jump into the topics today because we just have 45 minutes for this session. So what very specifically interests me to talk about cells for tractive application is the cells are everywhere. The various different chemistries of cells are available in the market. So you have LCO, we have LMO, we have NCA and NMC and LFP. Various types of cell chemistries are available in the market, right? So like the topic being that cells for tractive application. The meaning is what kind of cell chemistries are really suitable for a application to automotive. So it's a very comprehensive, detailed study that somebody has to do to select a specific cell for a specific application. So all of that depends upon various different operating parameters. The one is such as environmental condition, right? So we should know where all the cell is being used for. Maybe if you take a specific cell of any chemistry. So for example, if you take a mobile phone applications, right? So for the specifically in the mobile phone applications, you would see the battery discharge characteristics, battery temperature characteristics, its charge and discharge cycle. So you typically have a everyday charge, everyday discharge sort of characteristics, or any specific applications that has been used for, number of cycle life use count. Many of the parameters like this will play a very important role to choose a cell for a specific application. And each of those cells I'll not go more theoretical as we just draw a spider graph and show, okay, this has a more energy density, this is a more cell life, this is this characteristics and that characteristics. But typically, as far as this whole session is considered, to tell you that there are various different cell chemistries available in the market. So it's of your interest to choose that very specific right chemistry for a right application. So all of them have their own advantages, they have their own disadvantages. For example, if you take an LFP, which is a lithium ferrous phosphate based chemistry, so it's fantastic in terms of its stability, right? So it means it is less hazardous to catch a fire. And also it carries less, it is less energy dense, and because of that, the amount of energy it contains is also less. The scenarios for it to go worst in terms of safety is also very little in cases. So, but it is very good in terms of that. It cost is also very less, right? So, but the challenging scenario on the other side is the weight of the battery is a little higher on the side, right? And the cost is lower, but the weight is higher. So also the volume is slightly higher. So you need a lot of space to store the battery. You also have extra weight on the battery. But on the other side, you have better safety, you have lower cost, and better cycle life too. And better temperature operating wideness. So how do you choose a specific cell for a specific applications? So that's an interest for us today to talk about what all the parameters that you look for. So the first thing to understand is to start with, so there are various different cell chemistries. It's quite important to know and understand that the type of chemistry, its specific characteristics of it, its behaviors, its temperature and operating points and stuff like that. So specifically, there are various different anode material, cathode material, electrolyte material, separator materials. All of them do play a vital role, because if you see today in automotive industry, if any battery pack manufacturing was a tier one, something like Hexicon or something like a Bosch or Continental, who could supply the batteries to OEMs, they have a team of researchers who buy these batteries from Samsung or LG or Panasonic. They would procure those cells and conduct extensive amount of testing, extensive amount of activities where they can actually cycle a cell at various temperatures, cycle a cell at various different loading condition, store the battery at specific SOCs, operate the battery between various band of SOCs. So they would study not only at its characteristic level as the way it exhibits its behavior, but also they'll take that cell, they'll dissect it, they will see whether the stage of bonding materials between anode and cathode. A lot of these things, activities do happen at a core of industry. So to begin with, so various different cell chemistries, choose the right one which is applicable for your own requirements. So what industries are following through the market? So if you see Tesla, they've gone with NCA. So if you go back here, so you have NCA is basically nickel, cobalt, and aluminum. And they have also LFP chemistry that is coming in recent vehicle markets, specifically for Asia. So for the low-cost vehicle applications, they're trying to introduce LFP chemistry. And NCA is typically on the higher energy requirements. That is typically for all the performance vehicles. We're definitely still be coming with NCA. But for sure, on the application of an Indian market, they're trying to look for an LFP. So if you see an observance here, the cost is a challenge. They would prioritize LFP as a part of it. So if you see Mahindra, which you can just point out here as E2 as a platform, right? So they have used LFP. So LFP is more stable. It is more rugged in nature, and it is more controllable, because you don't want to end up having a vehicle which can catch a fire, right? So you may have an amazing cell technology if your knowledge on the assembly of the battery, integration of the battery, designing a safety circuits is not very good, then you possibly do not really want to go and touch in something like an NCA. NCA is amazing in terms of its characteristics, in terms of its abilities, But the problem is it's highly prone to having challenges for accidents, and or impact of the accidents can be very severe in nature. So you need to really safeguard the battery that well. So if you're not very, very well exposed to ensuring the integration of systems, making them work properly at an assembly level, so it's not definitely suggestible to jump in for NCA at a very preliminary level. You also see some vehicle manufacturers have introduced the performance vehicles with the chemistries like NCA, and a non-performance vehicle. So if you see like any vehicle as a bandwidth, you have a low pricing to a higher pricing model. So you have high performance side on the one side and the low performance side on the other side. So you could just say, okay, for this part of the vehicle, I would go with the LFP. So I would, for this side, I'll go with something in other chemistry as part of it. Some companies have definitely introduced these models also in the market. So there are other chemistries that majorly the industry has been following. Recent trends has been, if you see NMC chemistry, and specifically has been NMC has been used by Chevy. I've heard largely the LG supplies the batteries for this, and these are the pouch type of the batteries. I possibly have some images to showcase across. And the NCM and NCM is again taken by BMW. So there are various different type of chemistries are used by various OEMs. It is not only sometimes just the availability of materials, it also depends upon your supplier network, it's your pricing, your packaging requirements, your exposure to the design of systems, and various other type of exposures would definitely matter to go with the chemistry. It's always suggested if the technology is not very matured with you on safety perspectives, you may not have a very amazing and a top-notch technology to safeguard your battery. So it's okay to start with LFP. So then migrate to further other stronger chemistries. So there are various different suppliers today in the market. You could say LG, BYD, Samsung, Panasonic, and various other suppliers as such as Kettle, SK Innovations, and various other different suppliers are there in the market who typically supply any of the cells to automakers. So typically, none of the automakers would go for their own manufacturing of the battery. But typically, if you see something like Tesla, so they have been trying to enter into a market with their own cells. But yeah, if you see another side, the automotive never works in the same way. So you have tier one suppliers, you have OEMs, then you have tier one, you have tier two, tier three. This is a typical supply chain network that happens for our OEM. But some companies like Tesla, so they have a very different approach of making batteries and stuff like that. But it's fantastic if they could succeed. But certainly organizations like BMW or Mercedes or any of them may have been working definitely on cell chemistries in-house, but typically today, if you see largely, so they are buying cells from other tier one suppliers like Samsung or LG or Panasonic as such in the market. So let's just jump into some more technicals as a part of it. So if you take any part of lithium-ion cells, so they're available in specific formats. I'll come to that. This will be very basic to tell, okay, there is a cylindrical cell, there is a prismatic cell, and a pouch cell. The interest is not only that, interest is a little deeper than that. So if you take a different formats of cells, it starts with cylindrical, and then there is a prismatic and pouch cells. They have their own advantages. They have this one disadvantages. I'll try to jump into those points in detail so that we can understand if you're selecting a cell, how much does it matter really to choose a specific type of a cell in detail. So the one of the very major criteria is when you're forming your number of series and number of parallel configurations, all right? So, if you're planning about your battery pack size, for an example, it means the volume. So you may not have a very large volume in your vehicle to store the huge volume of a battery, right? So at that time, it's typically difficult to go for something like a prismatic kind of a cell. So you would definitely go for majorly on a cylindrical or a pouch. So again, the scenario is if you have a cylindrical cell, your cost of manufacturing, your assembly process is really, really complex. And also even for the pouch cells too, the assembly process and ensuring them, the contact between the current collectors and the whole cells in the modules are also very complicated in a scenario. So we'll talk about that down the line in presentations, but the point to understand at this stage is there are various type of formats of cells available. So which kind of a format would you like to go for in the market? So starting ahead with the first kind of a format, which is basically the pouch cell sort of it, which has been taken by many OEMs as an approach today. So if you see the complexity of any of these cells to integrate is, how do you engage these current collectors? So at a very electrochemistry level, you have a current collector, and so typically we use aluminum and a copper as the current collectors in lithium-ion batteries. So the point of it is, this is the output points of positive and negative. So you want to draw the current out of it, right? So if you would like to draw the current out of the cell, so a lot of parameters would involve. So what are the kind of parameters which will involve, right? How do you clamp another metal to draw the current out of this, right? So for example, if you take this, so if you take a portion of this cell, right, you need to properly engage the portion of the current collector to the bus bars, right? So the bus bars are the one which carries the current from the cell and make them as a whole module and then integrate them to a pack, right? So even the roughness of the surface of a current collector, roughness of the surface of a bus bar will matter really, really a lot. And also in a scenarios, what is the material that you're trying to use will be also very much of a matter. The approach of bonding methodologies, such as maybe, are you going to use a screw or a bolt? Are you going to use approach of spot welding? Are you going to use approach of laser welding? How are you going to bond these two inputs and outputs of the cell into a major bus bar, so where you can draw the current out of this, right? So these are very, very challenging scenarios. It's just not like, okay, there is a fantastic supplier in the market, you just go to them and select a cell. But it should be also, because they would not definitely give you an insight on how do you build a module, how do you build a battery pack, and what is the right module configuration. So how you can reduce the resistance, as a part of your whole battery pack, because right, like as you use bus bars, they also will act as a resistance in the module or at a pack level, correct? So if you do not have a proper series and parallel configurations, it will be very challenging even for you to minimize your resistive losses, or minimize, or also complexity in terms of cell balancing, and complexity in terms of thermal management. So you need to think a lot of these things at a very in-depth level to make your decision that how do you choose a cell. So it's not just at the characteristic level that you just take this cell. Okay, I'll go to a cell testing and characterization device. I'll connect this cell, and it is fantastically behaving. Not only that, you just also need to know a lot about manufacturing. All right. So the lot about manufacturing is just look a little deeper inside it. How is this cell is being connected to a bus bar? And this itself is more than one or two PhD studies, all right? So like in similar, we have complexities for cylindrical cells as well, all right? So if you see, Tesla has been using 18650 in the beginning, and then they moved into 2270, and now they are trying to move into other bigger sized cells, right? So they are used to have an approach called the wire bonding. So the wire bonding is a methodology where you have a major current collector, all right? So this is your current collector. So you take a very thin wire, right, which has been visible here or here, any of these cases, that you make them join, right, to the current collector and to the cell. So the complex scenario is that, how do you make this thinnest of that wire to get welded at a very precise temperature, at a very precise position, and also at a very specific strength conditions, right? Because if you pull it, it should not come out very easily. It should have a proper contact in when it is getting welded into the current collector of a cell, and then onto this side. So when you're a mechanical engineer, when you think in terms of the manufacturing complexity, anything that is precision will take more time, will take more cost, right? So it is going to be a very challenging approach to make this specific wire bonding approach to make it as a option for your current collection methodology. So if you are not a very matured OEM, or had not much time to invest on R&D for something like this, it is definitely going to be prone to failure, because it is not just easy to get that into that accuracy level in the manufacturing. It is really difficult to come to that far what Tesla has come. So and even if you see Aether, so they have also using wire bonding approach. They would have done enough amount of iterations, plenty of iterations even to come and optimize to the level where the robots can take care of seamless wire bonding approach. So the thing is, it is not just about a cell. It's not also about an approach. You need to think, how do you draw a current from the cell? Because as in India, we are more at application level. So we are not developing a cell, but we are buying a cell from a specific manufacturer, and you're going to take that cell and then use that cell as a part of your application. So all these things matter a lot when you're choosing a cell, because if you're a startup, you may not have an exposure for all these things, and then you're going to end up spending a lot of complexities and time in iterating these things. So that was about 2270 or 18650 approach for Tesla. They've been performing wire binding approach. But if you take a recent, the bigger cell, it's 4260, I believe. I'm not very sure about naming. They've skipped the wire binding approach. They're trying to go directly integrating the current collector to the cell itself. If you see a very close look at it, so you have one tab that is going to come here, then you have another tab which is trying to bind it all through this. So it's a very the Tesla definitely didn't have these things on the day one, right? So they even have amazing engineers, but they would have done a lot of iterations over the time of it, and then they have came up with something like this. So what this would do, this would reduce the complexity and of wire binding. So this could be more easy for manufacturing, and when it is easy for manufacturing, it takes less time. So then you have a PCM that you can call as a battery management system, so that you just engage that directly to the modules here, or else you'd have to run a set of wires all the way coming from the modules, and then they goes to the individual PCMs as a distributed battery management system module. All right, so this is at some level. And also, if you go to the selection of a cell for automotive application, if you select a cell, something like a prismatic, right, which is kind of visible to you here very clearly, so you would go for some kind of bus bars like this, or an iteration of different type of bus bars. So if you see here, this is a battery pack from Toyota Prius. So they have taken some of these outputs as positive and negative. All right. So when you talk about this, it's very important to know what is the the surface roughness of that material, and that it can just connect properly with the current collector or anode or cathode, right? So, and also it is so important even that what is the torque of this bolt, what is the torque of that nut also will matter a lot. And then what is the kind of reaction that can happen at the current collector will also become a very important thing. If you put a copper or any other material, it can also form some oxides of copper. Or if you put a very specific surface roughness, so it also matters a lot. So all these things need to be very well thought and brought into the knowledge of manufacturing Because, as I again said, in India, we are an application engineering concept as of now. We definitely wish to develop our own cells and chemistries as such, but a lot of research is going on. But right now, at a practical point of it, we are application engineering currently. So with that as a knowledge, all these things becomes a very important thing. What kind of cell are you selecting? Maybe this looks slightly easy, compared to integrating the pouch cells or cylindrical cells. So that's why you can see some of the OEMs in India would have gone definitely for a prismatic approaches. So I've done a comparative exposure study here on this. So where we're trying to draw, if you take many small cells, that means if you're going to take a lot of cylindrical cells, like what Tesla started with 18650, and now they're moving to very large sized cells, that it's definitely on the low cost cell in the commodity market, because you have a lot of the cells in the market. If you take, it's a proven manufacturing technology, because you have batteries or cells in laptops which are cylindrical in nature. They're coming from very, very long time, right? Maybe about 30, 25 plus years, right? Which are coming in all the laptop batteries. So that means that the manufacturing has been very well proven over the time of span. And the thing is, it is possible to achieve. So that's why you would have a lesser cost. So it is having possibly improved safety, because it is having a better heat rejection in terms of its surface area. And the problem is it need to have a lot of interconnects. It means you have to have a lot of assembly materials, right? One thing, let's say I told about wire binding approach, or directly, putting the current collector onto it, and then on top of it, you need to have a lot of these components, right? Where you can just position these cells at a right place. You can call them as spacers, all right? So on top of it, again, you need to have a very good amount of structural rigidity, because you have individual components. But the example I always try to give you is, if you take 9,000 bolts, let's say 7,000 bolts, and you try to put all of them together and weld them, all right, just as a mechanical visualization. It is so difficult to put all the cells and all those bolts together and weld them uniformly across the whole area which you're trying to keep those cells, all right? So the same way here, if you take that, it is very complex to think about manufacturing, a number of parts required, and you need to have thermal interactions to take a heat away from the cell. So all these things are complex in place. So obviously that going to be a higher cost on the manufacturing. Obviously, reliability, if you have more components, the reliability, you can also call it a redundancy of the system, would definitely reduce. So on the other side, fewer cells, the higher cell cost, and you have other options in place: increased reliability due to less parts, lower assembly cost because you have less number of cells, higher weight and volume efficiency because you don't have a lot of, if you take a cylindrical cells, right, you have some space that is going to be left out here in these regions as a part, that because you cannot put them together, you also need to give some amount of space between the cells because you can put your thermal management systems, right? So, but here you may not have that kind of a complexity. Your thermal exchange systems can be little definitely complex here too, and there is no doubt it is complex here too, because you have a larger surface area. When you have a larger surface area, you need to be having your larger pad area to take away the heat from there. And definitely other areas, better reliability because there are components which is mentioned there, and safety and integration in large system formats. Cool, let's jump into a few more quick topics. I just have another 10 minutes to go. So how you also select a cell? So until now, we have seen more on the chemistry side. We have seen more on the mechanical integration side of it. We will just jump into some more topics of it, which is basically on the characteristics of the cell. So where in terms of the cell selection, you need to have an intensive amount of study done to see what is the profile, specifically the current profile, where your cell is subjected to. So it could be discharging profile, or it can be also a charging profile. I hope you get it right. So the charging profile is can happen in two scenarios. The charging can happen through the standard charger, all right? The charging can happen also through a regenerative braking if you have implemented regenerative braking as a part of your vehicle. So your cell should be able to take that regenerative braking, and also the cell should be able to take your normal charging. And the second important scenario is the discharging characteristics. The discharging characteristics is not only your powertrain, it is also sum total of all your auxiliary loads. If you have a two-wheeler, you have a headlight, you have indicators, your horns, maybe your charging systems for your smaller batteries, smaller phones, or you also have an infotainment system and anything that is there as a part of your whole vehicle electronics. All right. So you need to take a consideration of all these loads to sum them up to be considered as your load on the battery. All right. So the graph which it currently show you as a part of your battery pack power that has been drawn from the pack. But if you know the voltage, you can just divide it, and P is equal to V into I. So you can just definitely get the current. So P by V would be I. So the graph would relatively come same, but just the values would change. So what exactly this graph tells you is you would have to know what is your uh, realistic peak power requirements, you can call it as a peak discharge requirements of the battery and a peak charge requirements of the battery, because you have a motoring mode where you're trying to consume the energy, where you have regen mode, where you're trying to put the energy back into the battery pack. All right. So when you're trying to do any of these scenarios, you should definitely study. How do you study? You can perform a lot of simulation studies that gives you a very comprehensive exposure to check what are the discharge characteristics. And also on top of it, you can perform a lot of realistic test cases, because in a product development cycle, we have an alpha sample, beta sample, gamma sample. So nobody just comes up with a vehicle and say, hey, just let's buy it in the market, let's sell it in the market. Nobody does it, right? So it goes through a lot of iterative development cycle. We start with the alpha sample where we can just build a few 5 or 10 protos, and then we can take them to the market, we can run them, we can test them, not to the market, out of the fields, and test them. We collect the data. We get to know what are the discharge characteristics of the requirements are. Then you can optimize a lot of your powertrain components, such as your transmission gear ratios, motor operating points, any of other things that you can definitely optimize in terms of your powertrain. So you can definitely have to have a very good, solid exposure to discharge characteristics. So the discharge characteristics would be the scenario such as current, right? So the first discharge scenario would be the current. So in that, you would know what are your transit requirements of the discharge characteristics. What is your this is positive, and the when you have a huge amount of regenerative energy, all right. So if you're not able to utilize that part of the regenerative energy, that may not be very much useful to have that regenerative energy. And also in other scenarios, what is the temperature at which you're trying to use the battery, and what are the typical SOC variations the customer can use the battery, and many other scenarios will come into a picture where the cell is being used. So you need to have the conceptual understanding of a lot of these parameters when you're trying to select a cell. So one of the very primary importance is the current, and the second primary importance is the temperature with which the cell is trying to be operated in the realistic world scenarios. So that's a very important thing. So you need to have a lot of data from your simulation engineers. You need to have a lot of data from the what I would say real-time test vehicles. So with all of that data, you would arrive at your characteristic requirements of the battery. So and then you choose some of the batteries from the market, and then temperature becomes a primary importance factor. So a country like India, we have a temperature ranging anywhere from 0 and up to like 44 degrees Celsius at damn hot summer temperatures. So in that scenarios where you would have severe impact on the characteristics of the battery. So when you have severe performance challenges then the battery would not exhibit the same characteristics what it can ideally exhibit at ideal temperatures. So all those scenarios would be taken as a part of it for the cell selection. So there are some data which I have uh, uh, which I've mentioned here as a part of it. So one of it would be discharge pulse power. So the discharge pulse power is you don't have a static discharge in EV. We have dynamic discharge. The meaning of dynamic discharge is the curve that is being followed. It means the current drawn from the battery is not linear in nature. If you take UPS applications, so you have a discharge curve, something like this, very much not variation in place. But if you take battery for EV application, the discharge is really high. So if you take I, and this is T, so the current drawn profile from the battery is slightly static in nature in a UPS application, like in a home UPS application. But if you take it for a EV application, the discharge is really dynamic in nature, right? So those are the things which is called as discharge pulse power. We have regenerative pulse power. And this is for the hybrid vehicles, so engine off, auxiliary load. So in our scenarios, so basically the auxiliary load in general, like an HVAC system, all right? So if you have turned on your air conditioning system, you will definitely use the energy from the battery, all right? So a lot of these auxiliary loads, if you put on the headlights or music system or any other electronics which is running for the cooling of itself, so would definitely have energy consumption. So recharge rate, the energy efficiency on load profiles, a lot of these parameters which are mentioned for hybrids here, so they also be the part of your EV requirements as well. So then moving ahead on the other side, the cells, when you select it, they are very specific to EV applications. This is a picture latest from Samsung. It has released a few cells in the market, I think just about 3 or 4 days. So if you see here that the BEV is specifically for a battery electric vehicle, and the cells for a PHEV is different. So the cell characteristics are very unique for a specific application. In that case, selecting a cell, you should be very conscious that whatever the type of battery you're trying to build, like when you call EV, you can call XEV. So it could be battery electric vehicle, or it could be micro hybrid, or it could be mild hybrid, or it could be something like fuel cell EV. So all of those specific type of EVs have their own requirements for discharge characteristics, their own requirements for charge characteristics in terms of the operating inside an hybrid or operating inside an EV. Or also, if you take any scenarios like hybrids, so there you don't have until and unless it's not a plug-in hybrid, the charging can only happen from regenerative braking or an engine charging. So engine being operated as a generator, right? So there are the only two modes: charge sustaining mode, if you want a charge depleting mode. There are various modes that comes as a part of the hybrids. So the only source of energy to the battery either is by regen or motor being operated as a generator. So engine pushes the energy to the battery by converting it. So in these scenarios, the discharge C rate, you can call it as, for the cell. So for the hybrids, HEVs is really large. So you want a battery that can discharge, let's say, up to like 10C or 15C, right? But if you take an application as EV, so in EV application, you would not go for this large discharge rate. You would go for possibly like 2C or 1C applications. Or at max in largely peak conditions, maybe like 3C to 5C. So this becomes very crucial in terms of selecting a cell for attractive application. So manufacturers have specifically defined cell for a EV application, cell for a UPS application, cells for an aerospace application, cells for an automotive applications. So on top of all these things, we have automotive standards such as AIS, and we have European standards, we have American standards, we have Japanese standards such as JIS or IEC, or you have SAE. Various different standards are there. So because the cell for an automotive application need to be certified as a cell for automotive application. So there are specific set of tests. You can just go to in website and type in EIS lithium ion in the standards for automotive application. You get a PDF, like Indian government has drafted some documentation to tell you like there is specific type of fire test, like nail penetration test or a shock test, vibration test. Various type of tests will come into a picture. So a cell, if you have to be used for automotive or an EV application, it has to be certified by AIS and in India. So like in similar, we have, I believe, standards for every different country. And you should select a cell which is certified to be what I say as a automotive standard. Then only you can use that cell for a application such as an EV. So I believe that's my interest to deliver the part of the whole session. So it's about 40 minutes. I believe it was interesting for all of you. If you have any questions, let's quickly jump into the questions, and then we can wind up the session maybe in another 10-15 minutes. Yeah. If something that I can definitely answer, I can definitely give some insights onto that, Vaibhav. Please do go ahead if you have some questions to ask. Right. So if you have any questions right now with the YouTube live, so we only have options via chat box. So kindly please drop it on the chat box. I'll try to read that and answer to you. So, all right, if anybody have any questions, so please do drop your questions on the chat box. And I believe session was useful, session was informative, and I believe it has brought some exposure to the parts of EV and selection of cells for attractive application. I'm very sure it is not everything what I was able to kind of cover up. But I'm sure there is plenty of so much to choose. But I believe what I was trying to kind of put across is it is not just so simple that, you know, in YouTube, some people show, okay, you buy a battery, you assemble it, and okay, the electric vehicle is done. Okay, it's fantastic. It runs on it runs on the road. A lot of very deeper engineering perspectives are there to make a battery pack, to just sell, to optimize your manufacturing process, and to bring it to so good level that it is under the cost where you can sell it. So how can we virtually simulate a battery pack in all aspects? We have options where you can definitely use simulation tools like 1D simulation, and or also integrate them with a 3D simulation, like 1D simulation in tools like MATLAB Simulink. You can perform models and then perform a lot of simulations. On top of it, you also have currently modules available from many suppliers. You can call them as in virtual cell simulators or cell simulators. They're very expensive, by the way. Cell simulators are, but you can start. If I don't know which, are you from industry, are you from academia? If you're from industry, you can go for cell simulators, or if you already crossed the level of simulation using the software. So first thing to begin with 1D modeling, that is using tools like MATLAB or Altair, Embed. There are many other tools as in similar. So you can use them to build the model. There are again many different approaches of building the model. You can definitely look more on that. We also have some courses on Decibels Lab to build a model, and then you can create realistic scenarios, and then you can perform a simulations. Or then the next level is you can buy cell simulators and stuff like that. Okay, so all right, thank you very much. I believe I could only share with my knowledge. Can we build lithium-air batteries coming in years? There is some extensive research on lithium-air batteries. They can be called as an equivalent to energy density of gasoline. Yeah, definitely there is some interest on that. Are EMC tests necessary? EMC comes as a part of an application that may not be required for cell, as far as cell is not integrated with the individual monitoring system as an electronics. That's an answer for Fayaz. Which type of cell is used in Tata Nexon? Maybe very specific. I'm not pretty sure on that. There are UI and two-wheel vehicles are also. I'm sorry. Okay. Electric engineer, what roles can we expect in EV? I think I would be able to answer you very clearly by end of this course. There are various areas where electrical engineers can involve. Specifically, when you talk about design of power electronics, we have chargers, we have DC-DC converters, we have battery management system, not be called as a power electronics, and also motor controls. And then we have control circuitries such as vehicle control unit, we have battery management system, we have a lot of other similar modules that come as a part of your whole EV. Then we have wiring harness design. Then we have control algorithm design for motor controls or battery management systems. And even for chargers, there is a control systems involved too. And then on top of it, we have a safety mechanisms, high voltage safety, and things like that. You can work on EMC and EMI compliance testing. You can work on testing and validation of the electric vehicle at a vehicle level. You can also work on testing and validation of motor controls, testing and validation of DC-DC converters and things like that. So a lot of these areas will be involved as a part of it. But I can give you some definitely deeper insights by end of this course. Great. So I'm currently working on converting petrol bike into diesel. 750 watt is suitable for a. For okay. Ajinkya Kulkarni attend the also like the last day of the course. We have a topic that is on Friday where you can build a circuit. Complete a vehicle in an Excel sheet. So our team member Krishna is going to teach that part of it. You can definitely decide on that day. All right. Okay. What's the buzz of a solid state batteries? I'm not very sure about solid states. I'm just trying right now to follow what is going on in the market with currently in application perspective. I'll surely check across and come on a few of these areas on solid state or lithium air batteries. Mechanical engineer, so there are a lot of opportunities for a mechanical engineer, so you can work on design of battery pack, thermal management of the battery pack, manufacturing perspectives of the batteries, integration of the batteries mechanically to the bus bars, and FEA studies for your battery packs. We can also work on design of motors. I mean, I'm not as electrical part of it, but also the mechanical part of it, and thermal management system for the motors, thermal management system for the battery, DC-DC converter design in terms of thermal management system. There is a lot of scope for design and thermal systems, and also CFD that is an derivative of that. So great. So what about time for charging and discharging also would life the battery? Definitely, the charging and discharging is going to matter a lot in terms of the cell's life. So if you discharge too deeply, if you charge too fast, you would definitely impact the cell's life. To go to that level, you would have to take a one deeper step to understand cell chemistry and cell kinetics and things like that. So where you will be able to jump in a little deeper step to understand, okay, if you do a fast charging, what really happens inside a cell? If you do a charging at lower temperature, what really happens? If you do a charging at higher temperatures, what will really happen? So all these things can be studied if you have some deeper exposure to the electrochemistry, ion transfer, or even the material construction and parts like that. So where you can go a little one step to see deeper what happens inside a cell when you charge it. So there is one session we have delivered for free, available on our YouTube channel. So certainly, please do look into it. Aluminum fuel cells, nano diamond batteries in the future. I believe so, Rishikesh. Thanks everybody for appreciating the session. Can we build a battery pack for using EV? Okay, I'm sorry. Can we build a battery pack for EV using alloy e-cells? I'm not very sure on that. SAS3. Apart from all, there are any kind of attendance for the session? All right, there is no attendance, by the way, for anyone. So we're going to keep the session in our learning lectures in our LMS. Then there will be a test. You have to clear the test, and then you can get the certificates. So how interview, how to ask questions based on this? All right, I'm sorry. Is that the question where what interviewer can ask you? I'm not very sure right now, Arif. Finally, a student in electrical engineering software we should learn in the future. There are a lot of softwares which you can learn. Decibels has recently hosted a lot of courses on design of embedded systems, where you can learn about LT-SPICE, which is basically circuit simulations. You can learn about ECAD, such as KiCad or Altium, or many other softwares. You can learn many other softwares which are used for magnetic simulations, such as Maxwell. It will surely depends upon some area that you want to explore. Okay, because it's so much of engineering. Maybe there is a magnetics, there is a low voltage circuit, there is a high voltage circuit, there is a design part of it, a simulation part of it, testing part of it, calibration part of it, a lot of these things. So I think if you sort of narrow yourself on what area do you want to focus on, it is more easier to choose what tools you can learn. Software which we need to learn and how fast charging works in differently than a normal charging. Okay, I think I'll cover that up, Sunadu, on the day of charging as a part of it. What about a control strategy for batteries? I will surely try to cover up that as a part of the tomorrow's session, Keshav. Any short courses on EV, Abhishek? Yes, we have some courses on EV that we will be like providing for the participants on a discounted prices. I think my team will definitely address that on the last day of the program, or they may write an email to you. At the charging station, same as a petrol charging station, they take money. Right now, they will be definitely taking the money for charging. We can use roof of car generate power by using solar pellets. Yes, it is feasible. There's a company called Sono Motors, SONO. So you can just check them on the internet. Sono Motors. They are trying to use that kind of a thing. It's called SOMOTORS, Sono Motors. And then also called Light Year or Light Speed. I'm just not very sure. Light Year, or it is also called as Light Speed. Both, I think, German-based companies. You can definitely check them. They are using something similar, using the roof of a solar and trying to generate electricity. How much time will it take to charge battery and EV? It definitely depends upon battery pack size. Maksud, Pranali, is there any software that we can calculate the number of cells that we can make a battery pack? Yeah, there is an option. We also have courses on that, Pranali. We can definitely do them in MATLAB. We can also do them in Scilab and many other softwares too. Yeah, even Tesla vehicles batteries are placed under the chassis. There is any protection for the batteries. Okay. Is there if there is an accident, if it hits the metal part, there is no damage is done to the batteries. Okay, I believe that's an answer. So Kung Fu, great. Does regenerative braking affects the battery life? It is not going to affect if it is designed very well and if the battery is kept within its charging limits. So it is not going to affect. If it is not kept very well within its charge limits, definitely you will have challenges, because it's a very short time of a span, you're trying to just push a lot of energy into the battery, right? That's why it's called as a pulse. So where the pulse duration is about 10 seconds or 5 seconds. In that short span, you're trying to push a lot of energy into the battery. And again, the lot is a relative definition, depends upon battery pack size. So it can be surely a variable factor. All right. Fantastic. So I think we come to the end of the session, which is on the thank you note. Thanks a lot, everybody, who participated on today's session. So I believe it was informative. I believe it was useful for all of you. Thanks a lot for your patience, for attending today's session. Thank you very much, and we'll look forward to engage in tomorrow's session on battery management system. I'll be addressing the session tomorrow. Any topics, any questions which I left today, please do ask them tomorrow. I'll try to address them. So great, and thanks a lot, everyone. Good night, for all of you.